Wait, what? You came back? Well, welcome back. This is ISE 5870 Resilience Engineering. My name is Mike Rayo, and this is the second lesson in the first module. Now we're going to get into what is resilience engineering. And in order to get into what is resilience engineering, we have to go past what is resilient performance. We talked about that a little bit. You've taken some reading on that. You've watched some videos on that. What is resilient performance? Now we have to think about what is resilience engineering. And as part of that, we have to think about what is engineering. And so we're going to actually start there. And then we're going to think about, again, what resilience engineering? And this actually was something that caught me unawares. I actually started as a chemical engineer, and as a chemical engineer, it's pretty easy to say, like, oh, it's chemical engineering. It's like chemistry, but it's actually making things go with chemistry, and I'm actually solving problems, and that is definitely part of engineering. But lots of different disciplines think about solving problems. And then I came to industrial and systems engineering, and honestly, I think there are a lot of folks in industrial systems engineering, and there are certainly a lot of folks that are not in industrial systems engineering, and certainly same thing with resilience engineering, that may look at these fields as not being engineering. So I really had to think about what is engineering, and maybe a lot of engineers go through this. So what you started thinking about engineering, it certainly is a problem-solving discipline, and it's similar to something like designing. And again, and engineering actually has to get into designing as well, designing being that idea of intentionally creating this creative art. And then we have to layer in this pattern-based part of it. And the patterns we use in engineering, they come from the sciences. So again, chemical engineering, that comes from a physical science, chemistry. You have mechanical engineering, environmental engineering, all of it bringing in patterns, welding engineering, patterns of how the physical world works. Now we have cognitive systems engineering, which is actually where I come from before I got to resilience engineering. We have resilience engineering. What are the patterns that we're using for that? And as we go through this diagram, we start seeing that you have this design, this is how we're actually, putting new things in the world. But in order to do that, in order to build out these technological capabilities, we actually use these patterns. We go to our pattern library. How do things typically work? And not just how do things typically work kind of anecdotally, but using some scientific discipline. How do we have confidence that there was rigor in running those patterns through their paces? So we're continuously doing these set of observations, and I'm using that word very broadly, to go understand more about the world. We're taking that understanding about the world, and again, this could be about the physical world, this could be about the socio-technical world, this could be about the psychological world, this could be about all these different parts and pieces. And by the way, when you bring together a system, a socio-technical system, an industrial system, a societal system, that has all of these physical world capabilities or attributes, but it also has people. So how do we also have to understand and have patterns about how people work as individuals and as groups and as big groups? So we're constantly going through our pattern base to then go bring something back to then apply to the world and solve problems in that way. And this is how engineering is different than other forms of design. And so if we are working in that way, if we are using a pattern-based practice, and if those patterns are derived from scientific principles, and actually if we're doing it right, we're actually feeding back into the scientific literature as well sometimes, then what we're doing is engineering. So as we think about out there in doing observations, this is an example of how to do that. Is you're starting with a hypothesis, and you're starting to specify a context. I'm going to put that in context, and maybe in that context I can start to see, and this is about a work system, so I can start to see a general idea of competence. I'm going to try to predict expected performance. That's getting a little bit more concrete. And now I can see, your prototypical performance kind of, and then I can see, oh, actually, how would it, if I formally talk about performance, how well should it perform? How fast, how quick, how capable, how reliable, if you remember that from the last video. And then we keep going. And now I actually go and look at actual performance, and then I can split it into fragments. I can start putting it much, closer down to what I'm actually seeing out in the world. I expected it to do this because of all the patterns that I knew. I go and see it. I collect my raw data. I go and say, ooh, how are my patterns doing there? How did my solution do? That solution which reflects these patterns. And I go up through the cycle, and it continues to circle that way. We talked about in resilient performance going to this perception action cycle where we can deconstruct, and it's not fully decomposable, it's not fully deconstructible. We can start to look at it from these different perspectives. How is the world detecting things? How is that system detecting things? How does it interpret what it's detected? Then how does it respond to what it's interpreted? We do this in our engineering practice as well. So we do this in our engineering practice as well. So in our engineering practice, we have events or issues that we need to solve. That's like event detection. That's research. That's getting out there and doing observations. That's, generative, experimental, doing field work, anything else, doing data, data collection. Then I have to analyze it. That's my interpretation. Now I want to start seeing these issues that I'm seeing in my engineering mind. I'm starting to think about them in patterns. What patterns am I seeing when I look at these events or these issues? They should align with some of the things I typically see, or I know I typically see in these systems. This helps me see a different way. Then from those issue patterns, once I know those, like, oh, when I see that kind of issue pattern, I have some design patterns that I can use. Now, are those design patterns absolutely going to work in this case? Unclear. But I have a chance. So then I can move through the design patterns, and those design patterns get translated into actual designs. From those designs, I go put that out in the world. Maybe I test that in a carefully curated place. Maybe I go test it right out in the real world. I go check, again, this is my perception action cycle. I check the world to see what my action, this is the design, the redesign, the implementation, all those things. How did it do? That runs my next round of research, of analysis, of redesign and implementation, of research, of analysis, of redesign and implementation. This is an engineering process, just as it is a design process. And again, the distinction here is what are the portfolio of patterns that are being used here. And as we're bringing in science, that's engineering. So we actually we play with games with this, and you actually have people. What is good engineering practice? What does that look like? What are all the hallmarks? And we put the X's on there, and it's a lot of fun. We're just going to skip that for a second and just think about, again. Let's recap here. Requirements for all engineering disciplines. Now, I talked about this first one a lot, formal scientific foundations. But it goes further because this is a pragmatic discipline. So we have tools and techniques and practices that make them more effective and accessible and less costly, especially over time. As we get better at engineering the thing, we get better processes. We get better methods. The thing that took us, lots of money and lots of time to engineer 5, 10, 20, 100 years ago, or maybe 10 minutes ago, maybe I have new tools now, so it's easier, more pragmatic. I have an explicit, repeatable approach to designing and architecting. And last, I'm explicitly dealing with the trade-offs in all of the above, and there are trade-offs aplenty to continue my work and continue to do it better. All right, so maybe now we have a baseline for what is engineering. Now, if you've been following along in our course, you know that you've been tasked with this Cook and Long case study about what they claim to be a case study of resilience engineering, and perhaps the first ever case study of resilience engineering. And the question I ask, and for those who want to play at home, hit this QR code, go out and look at that article. It's a fantastic one. But is it resilience engineering? Is it an example of resilient performance in practice or intended resilient performance? Because engineering doesn't always work. So maybe this was resilience engineering, but it just didn't work because it didn't result in resilient performance. Are there signals? Are there indicators of resilient performance? If you go back to the first video, we talk about what that means. And then second, is it an example of resilience engineering? Are they using scientifically grounded patterns in order to design, redesign, observe, reobserve their environment, and then make changes? And that's the underlying question for all of you. And let me give you a little bit of a hint. I think there's good evidence that it is resilience engineering. What patterns did they use? And as you're looking through these things, typically when you read about these things, especially in the scientific literature, when there's a pattern, there's a citation. Now, if we're not in the scientific literature, maybe it's a little harder to figure that out. But what I want you all to think about is, what are the patterns that you see there? But wait, what's a pattern? Just like, wait, what's engineering? Wait, what's a pattern? And what a pattern is anything that captures relationships. And those relationships evoke more than just the constituent elements, but it requires them. And typically when we're thinking in resilience engineering, these things are emergent. They come out of the environment. We don't necessarily design for all of them. So lots of things are patterns. Everything that we know of that's a complex thing. If I think about a person, that's there's lots of different constituents to a person, but there's some things that I typically know about a person. I typically know about how their eyes relate to sight, how their ears relate to hearing. I know I bring other things to it. I know generally how strong that organism is relative to other animals or other or even machines. But the question is, why do we use patterns? And the answer is, we're absolutely hardwired for them. And what these patterns help us do is they direct us where to look next and what to do. It also, we're hardwired to go looking for them as well. And you'll notice this from the example that this line plus these two squares, you put them together, you actually see this pattern of a horizontal surface, almost like folded paper. Is there folded paper there? Absolutely not. But I actually see folded paper there. I can see what is maybe intended by that design. This one at the bottom, I don't expect that you definitely know what these two patterns are. These two are ECG patterns of a heart rhythm. And even if you did know that one, I don't expect that you know which one of these is the healthy heart rhythm. But our clinicians know, and they know it quite easily. So when they look at this, they can very clearly say, this one on the left is normal sinus rhythm, and this one on the right is atrial fibrillation. So each of those are patterns. Each of those patterns help you to understand what to do next. In this case, maybe it's to walk a little bit faster to that patient on the right, and maybe not worry about that patient on the left. Again, does it say, run over here to that right one? No. But that's what I can draw from it because I see the pattern. And that brings a lot of other things with it. This is another pattern. This is the Cushing pattern, is what we want to think about. And the Cushing pattern is when our pulse rate, our heart rate, is decreasing, declining, and depressed. At the same time, our blood pressure is increasing and getting to critically high. This is not a typical pattern that's in our physiology. Typically, those two things don't happen at the same time. And what we ran was a quick study to see what happens, when different clinicians are exposed to this pattern of a patient they otherwise didn't know. And you can see all of those responses at the top. They didn't see the Cushing pattern. Oh, the blood pressure's going up, the heart rate's going down, but they're seeing that separately. So perhaps, again, what do I do next? I treat them both. I treat the heart rate, and try to get it to come up. I treat the blood pressure, try to get it to come down. When I see that it's a Cushing pattern, I do something totally differently. Because the Cushing pattern is a pattern that indicates increasing high intracranial pressure. So changing the heart rate, changing the blood pressure, that's not going to affect this intracranial pressure. And by the way, that's on the good-bad scale, that's a pretty bad thing. So we need to deal with that first. I need to deal with that intracranial pressure. That's the acute, the critically important problem with this patient right now. And if I don't see this pattern, I'm not going to understand that and respond till it's perhaps too late. So again, do these two data elements in isolation, do they tell me what to do? No. Only by seeing the relationship between the two of them do I understand what to do next. So let's bring that back to resilience engineering. In resilience engineering, we use these patterns as we go out and look at the world to see it perhaps a little differently, hopefully better. And we need to do that because we know that complex adaptive systems are sneaky. They hide what they're really doing. Now, that's not nefarious. It's just we know that the higher the fluency, the higher the expertise, the higher the capability, the more hidden what it actually takes to do that work is, even to those people doing the work. And so we need these patterns to be able to go in and just dive in a little bit deeper, dig a little harder. And this is an example of that. We did this with air traffic control. And in this one, we used patterns of workload management. When there's just high periods of workload, how do they deal with it? And how can we see the good and bad performance that we observed through the lens of that workload? And does that help us? And it didn't always help us, but in this case, it did help us quite a bit. And so what we know from a general pattern is there are actually very few distinct strategies on how to manage workload. You either do a little bit less, you do the same amount, but you do everything of a little bit less quality, or you move work around in time, or you recruit new resources. Those are really the four basic ways to deal with workload. Two of those are more tactical. Two of those are more strategic or anticipatory. And from there, if you're looking through the world in that lens, you can see all of these things that we actually, so there was never a big sign that said, oh, this is workload strategy 1, but we did see when there were things like reduced minimum separation between aircraft, what kind of strategies were they using? When we were seeing workarounds, now either workarounds in the physical environment about how they're moving aircraft around up in the air, also on the ground, how they're coordinating across each other, in maybe ways that are different than textbook, or even working around a piece of software. How are they doing it, and how did workload affect that, and how did their strategies and how do the observed behaviors reflect how they're thinking about workload management? And in that way, we could start to see, oh, this is what's going on in the work, and we actually the interventions that we chose, the new solutions that we chose to try to deal with that, to try to make the system better, to try to make the system more resilient, were much different than what we would have done otherwise. So again, let's go think about this case study. Hopefully you've read it by now. And not only do I want you to think about, is it resilient performance? Is it resilience engineering? Again, I think it is. But start doing the work. Start being that resilience engineer. What kinds of patterns are you seeing in there? I know your pattern library is, we're only at lesson 2 here. What do you already know about? What have I already said as general patterns? How are you finding these in the case study? Thanks. See you next time.